Hello, this video is primarily for Eric, and we're going to try and get you caught up on what we have been doing in discrete math lately. You had a worksheet last week where it was about exploring polar graphs, and I'm not sure if you actually did that or not, but what you were supposed to do was set up your calculator, enter some equations, and hopefully see what different polar graphs looked like. Today we're going to give you the official version summarizing what sort of equations give you what sort of graphs when you're working in polar form. And the first and easiest of the polar graphs was one where it said r equals some number, like r equals a. You might have something like r equals 7 or r equals 2 or anything of that sort. You have an equation that says r equals a. What you get is a circle that's centered at the origin. You get something like these two pictures here. The one on the left happens to be r equals 5, and the one on the right is r equals 2. These are like the circles that made the target on the polar graph paper that you used to graph points earlier. They're all different numbers of units out from the origin. It always turns out that whatever that a, that number is, that's always the radius of the circle. So the one on the left has a radius of 5, the one on the right has a radius of 2. The second type of equation that we looked at were ones where it had sine or cosine involved. You had things where it was r equals something cosine theta or something sine theta. And whenever that happens, you get a circle, but this time it's a circle that goes through the origin. On the graph, the equation of the circle that you see on the left would be r equals 6 cosine theta, and the one on the right would be r equals -5 sine theta. One thing you should notice is that if you have a cosine problem, it's always centered around the x-axis, and if you have a sine problem, it'll be centered on the y-axis. If you think about everything you've done before in trig, cosine always had to do with x, sine always has to do with y, and that's still true here. So again, cosine, it goes around the x-axis, sine, it goes around the y-axis. Whether the number in front is positive or negative tells you which side of the axis it's on. I said before the equation that you'd have to get the graph on the left would be 6 cosine of theta. Since it's a positive 6, it goes on the positive side of the x-axis. And the second one would be r equals -5 sine of theta. The negative is what makes it go down instead of up. Whatever that number is tells you the diameter of the circle. So if I had 6 cosine theta, the diameter is 6. -5 sine theta, I have a diameter of 5. The next kind of equation that we're going to look at is what happens when you both have a number at the beginning and you also have a number by theta. Things like 7 cosine of 8 theta or some problem of that sort. The shape we get when you have a number by theta is what's called a rose. Here are a couple of roses. I always kind of think they look more like daisies than roses, but you can kind of get the idea of a flower at any rate looking at both of those. On these ones, the equation that you're going to look at on the left, I believe would end up being 4 cosine of 5 theta, and the one on the right is going to be 7 cosine of 4 theta. It turns out that whatever the number at the beginning is always the length of each of the leaves or petals. So, when I had 4 cosine of 5 theta, I had a length of 4, and when I had 7 cosine of 4 theta, I have a length of 7 on those leaves. For the number of leaves, If you have an odd number at the beginning, there's always that many leaves. So 5 theta gives me 5 leaves. If I'd had 3 theta, there would have been 3 leaves. 9 theta would give you 9 leaves. If it's an odd number by theta, that's how many leaves you have. And if the number by theta is even, you always end up with twice as many leaves. This equation, again, is going to be 7 cosine 4 theta, but there's actually 8 leaves. There's twice as many leaves as that, and 4 times 2 gives you 8. Each of the leaves always goes through the origin, and the first leaf is always at 0 degrees in standard position. You can tell where the other leaves are because they're always evenly spaced around the circle. If you wanted to know exactly where they were, what you can always do is take 360 divided by the number of leaves, and that'll tell you where they are. It's exactly what you did when you were taking roots of complex numbers earlier. So like on the 5-leaf rows, if I take 360 divided by 5, I get 72. So those leaves are spaced every 72 degrees around the circle. One of them's at 0, one's at 72, the next one happens to be at 144, and so forth all the way around the circle. Question that I want you to think about for a minute is how could I get a 6-leaf rose? How could I get something that looked like what I've got graphed here? You might want to just pause the video for a second and ponder that, and then we'll talk about where it might come from. So if you think about it for a second, the way that we got even numbers of leaves mostly was to do even numbers by theta. But there's a problem there because when you had an even number by theta, you always had twice that number of leaves. If I had like 2 theta, I'd have 4 leaves. If I had 4 theta, I have 8 leaves. And every time it's double the leaves. So just using an even number, I can't get anything except a multiple of 4. What you have to do to get a 6-leaf rose is to actually use 2 separate equations. And I have those equations here. While the calculator was blinking, it actually sort of blocked off the fact that the first equation is 4 cosine 3 theta, and the second one is negative 4 cosine 3 theta. And if you put those together, you do end up with one where the first leaf's at 0 degrees, one where the first leaf's at 180 degrees, and you get like mirror images of 2 3-leaf roses that give you the 6-leaf rose that I had there. One other thing that you may have noticed is that all of the roses that I used as examples had cosine in them. And in fact, anytime you have to graph something for class, it's going to be cosine. But an obvious question is, well, what if it said sine instead of cosine? And I have one here that is 5 sine of 2 theta. You can see it's a 4-leaf rose, but the difference is that the leaves aren't centered around the axes. Here, I have them in the middle of all 4 quadrants. And it turns out that sine isn't necessarily what you'd think for where the leaves are. A lot of times people think that one of them should like be on the y-axis and they should be centered around from there. But what actually happens when you have a sine problem is the first leaf is actually always at 90 over the number by theta, 90 over b. So here it's like at 45. And then the rest of them are centered evenly around the circle. Again, you don't really have to know that. You're not going to have to graph one with sine, but that is a question people often have. The other main kind of equation that we're going to deal with are ones that have pluses in them, where it says something plus something else cosine theta, or something plus something else sine theta, a plus b cosine theta, a plus b sine theta. kind of graphs you get with these look kind of weird. They look like you either have a circle that like has an indentation on it, either at the side or the bottom, or you have a loop within a loop. The names of these shapes are cardioids or limacons. And the word cardioid should kind of make sense if you look at the first couple of graphs, because they kind of look like hearts, and you can probably tell that cardioid has something to do with a root that comes from heart. Limacon is actually related to lima bean, and if you look at the last two, they kind of look like limacons. Now, cardioid and limacon literally are the same shape, and there's really not a lot of difference between them. And different mathematicians will debate about which of these things are actually cardioids and which of them are limacons. The one on the bottom left, everybody calls a limacon, and the first two, everybody calls cardioids. It's the last one that kind of can go either way. But they basically both come from the same type of equation and they are the same type of graph. Both of these have a big loop, and then they either have an indentation or a small loop. And you can always figure out how far out the big loop goes by adding together the two numbers in the equation. On the two problems I have here, the first one happens to be 2 plus 2 cosine theta. The second one is 2 plus 2 sine theta. Once again, you can tell that cosine goes around the x-axis, sine goes around the y-axis, and with 2 plus 2, they both go out as far as 4. Now, on the other two, I have ones where they go out to 5 if you count them. The first one happens to be the equation 2 plus 3 sine theta, and the bottom right happens to be 3 plus 2 cosine theta. But both of those, you add up to 5, and that's why they go out as far as 5. So the big loop, you always just add the two numbers. I kind of purposely put it in the order b plus a, and we'll talk about that when we get to the other possibility on these. For the small loop or indentation, what you do is you subtract those numbers, and in particular, you subtract second minus first. Now, I told you before that on these first two, the equations were 2 plus 2 cosine theta, 2 plus 2 sine theta. Either way, if you do 2 minus 2, you end up getting the origin, you get 0, and that's where this indentation goes. On the other two, what happens when I have, again, the first one's going to be 2 plus 3 sine theta. So to find where the indentation is, I do 3 minus 2. That gives me 1. That's why I have a little loop that goes up to 1 inside the big loop that goes to 5. And the second one here, what I have again would be 3 plus 2 cosine theta. If you subtract those, you do 2 minus 3 and you get negative 1, which is why I go over to the left side for the indentation on that one. So again, subtract second minus first to figure out either where the inner loop is or where the indentation is. Let's quickly look at two other possible shapes. One of them is what happens if you do theta divided by some number, and actually the same rule would apply to theta times any number. What happens if I do, for example, theta divided by 75 is I get this little blip that you can see on the screen, which if I extended my window so that it went to 720 instead of 360, it's a lot easier to figure out that this is going to be a spiral. And here, what you want to do is keep on going. It'll keep getting bigger and bigger the further out you go. So again, if you have theta divided by a number, you're going to get a spiral. The last shape I want to talk about is what will happen if you have theta equals some number, like theta equals 45, or theta equals 90, or theta equals anything, really. What ends up happening if it says theta at the beginning instead of r is you're going to end up with a line that goes through the origin. Basically, you get one of those lines that was on the polar graph paper that you had to begin with that made up that big target for the polar graph paper. Here, I literally have what would be theta equals 45. And what you can see is that it's a line that goes right through the origin at 45 degrees. You do end up with that sort of graph. Now, you actually can't graph this in polar coordinates on your calculator. What I literally did is I went back into rectangular form and I graphed the line y equals x, which is the same as 45 degrees in polar coordinates. If you had like theta equals 90, what you would have is literally the y-axis, because you'd go to 90 degrees and you make that line. Now, any line like this, it is the entire line. Like the 45 one, it's both in the first and the third quadrants when you graph it. You do the angle, but then you also keep on going through the origin to find what's in the opposite quadrant. So obviously for the next several days, we're going to be doing some graphs with polar coordinates, or looking at graphs and figuring out what equation you have. And the big thing to remember is what sort of graph goes with what sort of equation. That's what we're going to be looking at here.